Hello everyone, and welcome to the first tutorial of a new series where we're going to be looking at how to use Python to teach mathematics and physics. So the first thing you're going to want to do is to make sure that you have the correct libraries installed for being able to do this. To do that, you will have to open a command window on your machine, and then we will use the Python installer packages with the install command together with the name SymPy, the library that we wish to install. Okay, so as you can see, I already have it downloaded, and really now all it's doing is installing it onto my Python environment. Okay, so once that has been completed, we can close the terminal and we're ready to start learning algebra using Python. As you may already know, SymPy is a really powerful computer algebra library which allows us to write symbolic expressions and manipulate these expressions using Python. So in order for us to start using SymPy, we have to import this library, and so there's many ways in which you can do this. Either we can import everything from SymPy. We'll do that by saying from SymPy import star. That just means import everything. Alright, so by running that command, you will see that it just gives me an output of 1. Typically this is advised against since it can easily confuse the namespaces in Python, but I can also call it as an alias. Alright, so in other words, I can import SymPy as SMP. So now we are ready to start doing some algebra, and as in the first example, I will just declare the variables x and y by referring to the SymPy library and calling the method symbols, and then passing in the symbols which I would like to associate with that keyboard values x and y. And upon running that, it doesn't seem like anything actually has happened. But we can now start to write algebraic expressions, and so in this example I've given it the name expression, which is equals to x to the power of 2 plus the square root of y. And so to make sure that it understands the square root of y, we have to refer to the SymPy library. Okay, and so upon running that expression, it's stored to memory, and if I now want to do something special like a substitution, all I have to do is to refer to the subs method and then specify 2 arguments, the variable that I'd like to substitute together with the value that I'd like to substitute it by. So in this case, I'm just going to substitute 2, and I should get the identity 4 plus square root of y. So that's 2 to the power of 2 because x has assumed the value of 2, and then we still have to add that to the square root of y, which I haven't actually substituted, but we can go further and substitute both values. So if I want, I can substitute x with 2, and I can concatenate that with the substitution of y equals to 4. And upon running that, I should expect a numeric value of 6. Alright, so I also want to point out that this original expression is still available to us as it is unchanged, because the substitution was only an instance of that expression upon assuming the values x equals 2 and y equals 4. So nothing about the original expression has actually changed. To write fractions in SymPy is actually quite easy. As an example, we will just write the fraction 1/2, and you do that by calling on the SymPy library and then the method rational, passing in the first numerator, and then you pass in the denominator. Upon running that, I'm going to get this expression of 1/2. Okay, so that allows me also to define irrational exponents, in other words, surds. So for example, if I want to write the expression the 3rd root or the 5th root or something of that sorts, I will have to write the variable or the base to the power, and then in braces I can define the exponent as 1/3, and so upon running that I should get the 3rd root of x. We can also write standard functions and known constants. For example, if I want to write the constant pi, I can just write sympy.pi. I can write infinity as well, for example, smp.oo. I can also write the exponential function, pass in a symbol x, as long as that symbol has been declared before. And if I want to, for example, just write the constant e, I have to pass in a parameter 1 in the exponent, and so I just get e. Okay, I can also do trigonometric functions, for example smp.sine of x, smp.cos x, SymPy.tan x, and then obviously all the reciprocals for that. I can do the arc functions, so a sine of x, that's arc sine, SymPy.arc cos, meaning inverse cos, SymPy.arctan. I can also do logarithmic expressions. So for example, log x, that is the natural logarithm x. So in other words, the base for that is e, but I can change the base as long as I specify I want it to be base 10, but it will just obviously use the algebraic properties for the logarithmic functions to rate it as a fraction. I can evaluate numerical expressions to a certain number of decimal places. For example, that expression of square root 2 pi can be evaluated by calling the evaluate float value method. To a certain number of decimal places, I have to specify that. So for example, if I want to evaluate that to two significant figures, I just have to pass in the value 2. Okay, but there's more ways in which I can do this. For example, if I want to evaluate the constant pi to a certain number of decimal places, I can do that using the float method as well, instead of using the eval_if method. But I can then also restrict it to, say, a certain number of decimal values or significant figures. So in that example, I want 2 significant figures. And yet another way of doing that same thing is by calling the SymPy numeric value to 2 significant figures. We can now start to do some symbolic algebra. So for the first example, I have an expression x plus 1 to the power of 2. So that means we have to expand this set of brackets, which we can do by calling the expand method and passing the expression name. And so you can see it gives me the expanded version for that expression. I can also do interesting things, like if I'm given an expanded expression like that, then I can also factor it. So it just returns the factored version of that expression. All the terms which contain similar powers of y. Okay, so it has basically placed y cubed first, then it grouped this first and last terms together and factorized y squared, and then it factorized the second and the third one together, and it factorized y. Okay, we can also work with exponents. So for this example, I have a power expression. In this case, I should also again declare symbol a. So symbols a and b as well. So a and b. Now I get this expression. If I want to write a more compact version of that with the same base, I can call powers imp. We can also do logarithmic manipulation. So for this example, I have log x times y, and I want to expand that. So I'll call SymPy expand underscore log method, and that'll not really seem to have done anything, but I can force this term to be expanded by passing in parameter force equals true, and then it actually writes it as the log of the product is the sum of the logs, right? And we can also then go in the opposite direction. So for example, if I'm given an expression of sums and differences of logarithmic expressions, then I can combine those. If I try to combine it by calling log combine and it doesn't seem to give me the correct answer, once again I can force this by passing this extra parameter force equals true, and then it gives me this expression over here. Okay, we can also do trigonometric manipulation. So for the first example, I have expression underscore trig, which I set equals to sine squared x plus cos squared x. But if I want to simplify that expression, I must make sure to call on the method trig_simp, which is simplifying trigonometric expressions. And then there's a whole bunch of other things that I can do. So for example, a more complicated expression with factorials, I can call on the combinatorial simplification method to simplify the expression above, and that just reduces to that factored version over there. I can work with binomial expressions, and I can also call, say, a more complicated binomial expression, which I know should be able to simplify. So I'm, again, as an example, just going to call the combinatorial simplification method, and that just reduces the previous expression to x plus 1 over y plus 1. Okay, so that's quite a lot of things that we can do. Next, we're going to look at algebraic equations, specifically of one variable. We'll look at linear systems of equations. We'll look at nonlinear systems as well. We still have a lot of work to do. Okay, but for now, let's look at basic algebraic equations. So if I declare symbol x, which we've already declared actually, but just in case you don't remember how, here's another equation that I'd like to introduce. I'm going to call that by calling the library SymPy.eq for equation with capital E. And I'm assigning that to the name equation 0, and the equation is read as x squared minus 3x plus 2 comma 0. That just means I'm setting the expression on the left and I'm setting the expression on the right as 0. Then I'm going to call the equation so you can see it on the screen, and then I want its solution. So to get its solution, I equate the solution to SMP.solve, and then I pass in the equation name, and I also pass in the variable that I'm solving this equation for, and then I'm printing the solution to the screen, so I get this in a set of braces. So it gives me two solutions because it's a quadratic equation. I get 1 and 2 as a solution. Alright, here's another example. Equation 1, same thing, call the SymPy library dot equation method. I pass in the left hand expression, which I set equals to 0. Then I call the equation 1, which looks like that. And if I want to solve it, in this case, again, the same thing. In the solve method, I pass equation 1 and the variable I would like to solve for. And this time it gives me two imaginary roots, minus 2 minus I and minus 2 plus I. Those are the conjugates. Here is a cubic expression on the left, a 0 on the right. And so if I want to solve that equation, I'm going to call it solution 2. And it gives me 3 roots. So I've just chosen an example which gives me 3 real roots. Here is another cubic equation. If I solve that equation, it gives me 3 roots, 2. That's the real root, and then the two conjugates, minus 1 minus square root 3i, and minus 1 plus square root 3i. Okay, let's look at more abstract equations. So for that, I have an example where I introduce symbols a, b, and c, because our equation will be the general form of a quadratic equation. So that's what I mean when I say symbolic, is that all the parameters of the equation and variables are not necessarily known. And so I'm going to call solution 4, and this gives me basically the quadratic equation as a solution. Here's another example where I'm going to show you how to do a cubic solution. For that, I've called equation 5. And so the interesting thing here is that we haven't really looked at yet is that I can also use underscores when naming my variables or my symbols. I have a subscript 0, a subscript 2, a subscript 3, etc. because that is what I will be using as parameters in my cubic equation, and that equation returns this form. And so if I want to solve that, really not much is needed in the SymPy library and the solve method. And you can see this is quite a complicated expression, which you won't be referring to this a lot. Let's look at systems of equations. And so the first example is my two equations, equation 100 and equation 200, which I've declared in the exact same way as before. I have two equations this time, which include two variables, 5x plus 5y minus 7 equals 0, and 6x minus 4y minus 9 equals 0. So basically this was a linear equation where there was 7 on the right hand side, and the second equation has 9 as constant on the right hand side, but I've just transposed those and set that equation equals to 0 on the right. Let's actually first just see what the equation looks like if I print it versus what it will look like if I only call it like that. And so you can see it looks a bit better if you just call it. It looks much more rendered. And so if I now want to solve that, I'm going to do the exact same thing as before, but this time I have to pass in a tuple of equations, and I want to specify that I want to solve it not only for x but also for a tuple x and y. So then I'm going to print that solution, and it just returns it as a dictionary. So if I want to extract those solutions, I can then refer to my solution with the index key, so x, and I can also refer to the y value, and I get that. Okay. As another example, here I have equation 300 and equation 400, a nonlinear equation x squared plus y equals 0, and a linear equation x minus y equals 0. So if we want the solution, we are also going to pass in the tuple to the solve method, together with the tuple x and y variables for which we have to find the solution. And then also I'm going to set dictionary equals to true. That means I want to return the solution in a dictionary format, so like that. I want the x value of the first element in the dictionary. I can also extract the y value, and then again the same for the second half of the solution. Since this is a nonlinear equation quadratic, it should have, well, 4 solutions in total. Okay, so yeah, I can have 1 and x, and I can also have 1 and y. We're now going to start looking at some linear algebra, specifically matrices. And for this example, I've declared a couple of symbols that I might need to define my matrices. And so the first example that I have here is a 2 by 2 matrix, which I define by calling on the SymPy library and then referring to the matrix method. And so in the braces, you will see a set of square braces, which I use to define the matrix, and then another set of square braces to define each row. So this will print out the matrix 1, 1 with row 1, 1, and the second row 1, 2. But I can also define matrices with different dimensions. For example, a 3 by 2 matrix in which I have 3 rows, 1, 1, and then the second row 1, 2, and the third row 3, 1. And I can also have 2 by 3 matrices. So for example, 1, 1, 2, 1, 2, 3. I can have column matrices. In this example, I don't need to include a first set of square braces to declare that it's automatically understood as a column matrix without the square braces. If I wanted to define a row matrix, I have to include another set of square braces inside, and that'll give me a row matrix 4, 1. Okay, but for practical purposes, I will also declare this matrix over here a column matrix with variables x and y. And perhaps just as a last example here, I want to also define a matrix of 3 variables as a row matrix x, y, z. Okay, so we can also declare identity matrices. So in this example, I have a 4 by 4 identity matrix, and I do that by calling on the SymPy library and then referring to the method I, as in the optical organ in the human body, and then passing in parameter 4 for the dimension of that identity matrix. And we are now ready to start looking at matrix operations. For that, I'm just going to define 2 more matrices as an example to illustrate how we would work with the operation. So if I want to show you how V looks like, it will just be a column matrix over there. And then I can do substitution. For example, if I want to substitute one of the variables u underscore 1 with a value 3 in the matrix U, then I just use the subs method. Okay, and then it just returns to me that new matrix over there. But once again, if I refer to the original matrix, it should just give me back that original indices U1, U2, U3. But I can also refer to the indices inside of a matrix. For example, if I have the matrix M, 3x3 matrix, and I want to get its index at the position 0, 0, then it will give me this one over here, that little one, the first entry. I can go through a whole list of this to get all the entries one by one. Okay, and of course I can't pass in here a value of 3 because that just doesn't exist in the matrix. Okay, so let me just change that to the second row, the first column. That should return this 2 over here. If I want, I can also get the second row and the second column entry. I can also get second row and the third column entry, and so on. Alright, I can find the shape of the matrix, so it will return to me its dimensions. It's a 3x3 matrix. And then we are now ready to look at matrix addition. So how would we add two matrices? Here's an example. We've already defined the matrices U and V, so I'm just going to add these two together to show you that we get the result U1 plus V1, U2 plus V2, this is a column matrix, and U3 plus V3. Okay, how about matrix multiplication? So in this example I have already defined 3x2 matrix M. Alright, but I'm just, for practical purposes, redefining that matrix again. And then we also have the matrix V, which is a column matrix. But I can now go ahead and multiply these two together as in matrix multiplication to give me this as a result: x plus y, x plus 2y, 3x plus y. Okay, but of course if I had changed this to our 2x3 matrix, which we've already defined before, that will not work because of the way that matrix multiplication is defined. Alright, so that wouldn't make any sense. And so yeah, we can also look a little bit deeper into vector algebra. For this example, we will just look at calculating the norm of these matrices. So let's look at how to calculate the norm of U. You would just do that by calling on the method norm, and automatically it will give you this as a result. I can also calculate the norm of V. That's quite easy. So this is all symbolic. We can also look at the dot product of U and V. So I have two column matrices and I want to get their dot product. I just call U dot and V. I can also calculate the cross product by again using the method dot cross. So U dot cross V, that gives me this result. That again is a column matrix. Okay, and so this is all useful because I can then start writing matrix equations. Next we're going to look at solving matrix equations. So for that, let us just define the 2x2 matrix, and then we're also going to need to define the vector column xy as well as the constant matrix for 1, so that we can then define the matrix equation, which has this form. As you can see, I'm just using the same method as before, the equation method on the SymPy library, and inside of this braces I have the 2x2 matrix multiplied by the vector column, and I equate that to the constant column matrix. Okay, and so I get this equation, and if I want to solve that, I can just pass the matrix equation into the solve method and specifying the column vector xy for which I want to solve the matrix, and so it returns the result as x is 7 and y equals -3. I can then extract the solutions by referring to the key value, and the same for the y value. I can extract the y value as solution y. Okay, so next, quite interestingly, we will define a method for checking if the equation, the matrix equation, actually has a solution to begin with, and if it does, it will solve the matrix equation for us. Okay, so to do that, I've written this small short piece of code which I will explain. So I've defined the function called check solution or solve, and then it takes 3 arguments. The first argument is the matrix as well as the vector matrix, so the column vector x, y, or if it was a 3x3 matrix system, it would be x, y, z, whatever the case may be, and then also the constant column matrix. As we have done over here manually, we will then just pass this in to our solver function. What then happens inside of this function is that we create an equation using the SymPy library, and using the equation method, I define the equation by multiplying the vector matrix with the matrix and then equating that to the column matrix. It then finds the solution for us, and then it checks if the solution is either empty or not. If the solution is empty, it will just print no solution. Otherwise, it will run through each solution and give us all the solutions in our browser. It will print the solutions for us. So by defining that, I can now sort of better automate the matrix equation method. So here I have an example where I have a matrix, a 2x2 matrix 1 1 1 1. All right, I then give it also the vector matrix xy, and I also give it the constant column matrix C. Okay, so to employ that method, we will call on the function that we've just defined, and we pass in the 3 parameters: M for matrix, V for vector matrix or vector column, and then C for the constant column matrix. And then if I just run that by pressing Shift Enter, it'll tell me the solution is 1 minus y. That means we actually have infinitely many solutions, okay, to this matrix equation. I'm sure you all understand what that means. It is a prerequisite. Here I have another example where the system of equations will have no solution at all, just to demonstrate that this function will give us the output no solution. And so the system of equation is solved or checked for a solution by employing the method check solution or solve, and then I pass in the three arguments: the matrix, the vector column, and then the constant column, and it just says no solution. Okay, so that's a cool little program. And now I have another example of a 3x3 system with one specific solution. So I have a matrix, I have the vector column x, y, z, and I also have the constant column matrix with values 1, 2, 3, and I employ that method check solution or solve by passing in the 3 arguments: matrix, vector, and then column. Okay, and it just gives me the solutions 0, 1, 0. That means x is 0, y is 1, and z is 0. Okay, cool. Okay, so we are now at a point which we're going to be looking at calculus. And for that, we're going to start off by looking at more details of series expressions, okay? And then we're going to look at limits, derivatives, and integrals. Let me just introduce symbol n, SymPy.symbols, and I want to declare symbol n. In this case, let's say, for example, you want the sum as n ranges from index n equals 0 to infinity for 1 over 2 to the power of n. Okay, so by running that, you get the expression. The problem is that it did not evaluate it, so to do that, we just have to pass in the method to that expression dot do it braces. Okay, we can also evaluate that numerically by just passing in this method n braces for numeric, and so it's going to give us a floating value. We can also write partial sum expressions, and for that I have to declare the symbol k, and I'm going to use the same expression as above as an example, but it will only evaluate up to k terms, so it gives me this as a result. But once again, if I wanted to evaluate that expression, I have to pass in .doIt as a method. Okay, and so it gives me this expression. And that makes sense because now if you take the limit as k tends to infinity, then this should result to 2. Okay, if I had evaluated numerically that expression, it will just return 2. Okay, as another example, let's look at the geometric series 1 over n. Alright, but if I want to then go and do it, it should diverge, so it should give me a result of infinity, which means that it diverged. Here's yet another example, which is an interesting one because this is the summation expression for the function e. And so if I want to just check if that is correct, I can do it again by passing in that method, by calling on the method .doIt braces, and so it returns e to the power of x. That's not really surprising. We can also write limit expressions, SymPy sin x divided by x, for which we want to take the limit. So I'm going to just take that exact same expression and I'm going to put it into a limit like that, and then we want the limit to be from x to tending to 0. Alright, so if I run that, I should get a result of 1 because it already evaluated the limit for us. I can also specify the direction from which I want to evaluate the limit, so by passing in an argument direction equals plus, we'll evaluate the limit from the right. I can evaluate that limit from the left by specifying negative. I can also work with abstract functions as long as I specify that the symbols that I'm using in this example, f and g, are functions, and I have to specify that inside of the symbols method where I have the attribute class which I equate to SymPy.function. And so upon running that, again, it seems as if nothing actually has happened, but I can now go ahead and define my functions. In this case, I will define f as a function of x, and I will call that f. And so if I run that, nothing again seems to have happened, but if I then run f, I get back f of x. We can also do function composition. So for example, I can define g composed with f as g. So if I run that, it seems as if, again, nothing has happened, but it's just stored as memory. But if I call g, I get this expression. We can also write abstract functions of two variables. So for that, let me just introduce the symbol h as a function, and then in this case we want to define h as a function of x and y. Upon calling y, we get this. We can also define piecewise functions, for example this one over here, but it's quite tricky. So according to the SymPy documentation, the conditions are evaluated in turn, returning the first that is true, and if any of the evaluated conditions are not explicitly false, then the function is returned in symbolic form. However, if the function is evaluated at a place where all conditions are false, then it will return not a number, NaN. Okay, so what I mean here is that we have to be very careful where we place last condition where we want to test for equality, x equals to 3, or x equals to anything other than less than 3 or greater than 3. So to illustrate that, I'm just going to copy the exact same function, and we're going to move this last tuple to between these two. The documentation also states that the pairs where the conditions is explicitly false will be removed, and no pair appearing after the true condition will be retained. So this condition over here will be lost completely. So to illustrate that, it just will ignore that. So you have to be really careful. If you want to define these piecewise functions, you have to do it really correctly for it to work. Okay, so I have here another example which I think is worth demonstrating. So for example, let us define this piecewise function g piecewise by calling on the SymPy library and then referring to the method piecewise. Inside I have the function that I want based on the condition that x is between 3 and 4. And then if x is greater or equals to 4, I want it to return the value x squared. Otherwise, it should always return -1. So once again, I have to make sure to include this else condition at the very end of the piecewise function, okay, to obtain that as a result. So once again, as an example, if I had written this true otherwise condition anywhere else, then anything after that condition would have been rendered useless. So as you can see over there by demonstration. Okay, let us now turn our attention to derivatives. So as a first example, we're going to find the derivative by calling the diff method, and then for the function, for example the exponential function, I have to specify with which variable I want to take the derivative. Alright, and so obviously, as we all know, the derivative of the exponential function is just the exponential function. But if I had, for example, I'd specify a different variable, it is equivalent to taking the partial derivative of that exponential function with respect to y, which will return 0. Okay, so I can do derivatives, I can do partial derivatives, and here's another example for a polynomial expression. This polynomial expression, x cubed plus 4x squared plus 3x minus 5, we can take the derivative for that function, and I'm going to call that expression underscore derivative. And I'm going to define that as differentiating the original expression with respect to x. And then I want to display that to the browser as well. Okay, so I get the polynomial derivative 3x squared plus 8x plus 3. And I can also take the second derivative for that function. So let us call that expression second derivative. And I'll do that by differentiating the original expression with respect to x and with respect to x again, and I want to then display that to the console, and I get that. Okay, so it already factorized it, but I can also evaluate derivatives at a specific point. So for example, if I want to evaluate the expression derivative at 0, then all I need to do is to substitute x with 0, and I get 3. I can then also do symbolic derivatives as we did before with the symbolic function f. So for example, when we defined the function f as f of x, I can then go and compute its derivative with respect to x, just like that. Okay, the power of the SymPy library becomes really apparent, because you would notice that if I define this composite function g, and I then want to take the derivative of g with respect to x, that it will return the expression which already applied the chain rule. So as you can see, that is quite a powerful computer algebra library which is capable of doing such extreme techniques. As yet another example, let us define h as h of x plus f, and if I want to take the derivative of that function h with respect to x, it returns this expression, and it automatically does the substitution of the bounds for us. Alright, so it does the substitution at that value of x for us. Here next we have a more concrete example. So the expression f is 4xy plus x sine z plus x cubed plus z to the power of 8y, and I can then differentiate this function with respect to any of those variables. Differentiate with respect to x, then it returns 3x squared plus 4y plus sine z. Okay, so that's interesting. We can also do integration with SymPy, different types of integration. So the first integrals that we will look at is antiderivatives or improper integrals. In this example, I will integrate the function sine x with respect to x, and as expected, the result is negative cos x. In this example, I have an expression log x squared, which I integrate with respect to x, and that's the result that it returns. So that's an antiderivative for this function log squared x. Okay, but we can also do definite integrals. What that means is that the lower bounds are defined. Okay, so as an example here, I have the expression 1 over the square root of 1 minus x squared. I want to integrate from the lower bound 0 to the upper bound 1. And it returns the result immediately as pi over 2. But we can also evaluate indefinite integrals. Alright, as an example over here, we will evaluate the expression e to the power of negative x squared minus y squared between the lower bound negative infinity to infinity with respect to x, and then from negative infinity to infinity for y. So that is an indefinite integral. Okay, and that returns as expected the value of pi. There are techniques of evaluating that expression. You can use polar coordinates, convert this integral to a polar form, and then evaluate its integral. Okay, but we can also do all of this symbolically. So that is once again the power of the SymPy computer algebra library. So as an example over here, let us integrate the function that we previously defined as f. Okay, so this function over here, if you recall correctly, that's just f of x. But we can also integrate that symbolic expression, and it just returns this beautiful LaTeX rendered object. Okay, so I'm sure as you all know, according to the fundamental theorem of calculus, I have here defined f as the integral of small f. Okay, that's normally the standard way of expressing the relationship of a function and its integral. The only difference here, I don't have the entire theorem stated out, and also didn't include the integration constant. Be aware of that. I then also want to illustrate that if I introduce a new symbol t, that I can symbolically integrate f with lower bound 0 and upper bound t. Okay, and I can also do indefinite integrals in a similar way symbolically. Once again, as long as the upper bound or the lower bound is infinity, then yeah, I have my indefinite integral over there. Okay, so that's cool and all, but what about repeated integration? So that's something that we're going to look at now. And so there's many reasons why we would want to repeat integration. Depends on the region of integration. Perhaps you have a reason to do so, and voila, there you have it. Okay, so another way of doing that is by integrating with respect to x from the lower bound 0 to y, and then integrating with respect to y after from lower bound 0 to some symbol t. In this case, I've just declared t, so that gives me this expression over here. Okay, so I have a double integral defined over the integrand f, integrated from 0 to y. You then replace the values of x in the expression of f with y, and then you integrate with respect to y, and then you substitute your lower bound 0 to t. Alright, and so we can also do integral transforms, and a lot of you may not be familiar with this, but they are quite powerful mathematical tools to know, so I'm going to discuss them just in short. Integral transform. So my favorite integral transforms include the Laplace transform and the Fourier transform. Okay, so for this example, I have a symbol a, and then I'm just going to integrate the expression exponential function to the power of ax. So a is just a constant, that's e to the power of ax, by calling the transform method on the integrals method, and then the Laplace transform method on that transform method. And so by integrating that, that is the correct answer. So what this states is that I get the result 1 over negative a plus s, as long as x is greater than a. Okay, so here's just another example of that with a different function, sine ax. And once again, that's just going to give me a over a squared plus a squared as long as x is greater than 0. Okay, so that's interesting and all. But I can also get a symbolic answer for that by just replacing Laplace transform with Laplace transform capitals and no underscore. So that gives me this expression. So that's just understood as I'm taking the Laplace transform of sine AX. And then upon that, I substitute S. Alright, so it's just understood as a symbolic representation of the Laplace transform. Okay, so for the next example, we will look at the Fourier transform, which is just as amazing as the Laplace transform. Okay, so the Fourier transform, and anyone that has ever encountered differential equations should understand the beauty of these expressions. Okay, here I have the Fourier transform of the function f, and here's another example, the inverse Fourier transform. Okay, so really nothing special over here, just to illustrate the power of the SymPy computer algebra system. Okay, so I'm going to call it a tutorial, and I will see you in the next one.